Welcome to the WBAY WPNE transmitting facility. This facility was built in 2000 to take care of the change from analog to digital transmission. This building was built purposely for the DTV system that we have today. As we come in here, to my right, over here, is the Wisconsin Public Television's digital transmitter. Now it is completely solid state. If you look at the top of the cabinet, you'll see each cabinet has an independent output, goes into that tangle of plumbing above, which is called a combiner. Comes out of the combiner, goes into a special filter called the mask filter that helps shape the digital TV signal so it doesn't cause interference to adjacent channels. Then goes into a transfer switch. They either go to the dummy load or go to the antenna. On the other side of the room, you can see racks of equipment. Those are related to our microwave systems that bring in our microwave programming into the transmitter facility, and also brings in our remote news gathering antennas. And that equipment's associated with DTV news and programming. As we come in here a little bit further, you'll see all this plumbing above here. Well, this is the same thing that you were seeing over here with Wisconsin Public Television, except this is a lot higher powered. And as such, a lot of the components in it are waveguide. And so anyway, this is called a Magic T. It serves as a power combiner, and it also switches transmitters into a dummy load, so each transmitter can be monitored independently. This big thing up here is harmonic filters and the mask filter, which goes down this way. At one point we had 3 television stations operating in this antenna at one time. The big one on the end is associated with channel 3. The one that's not being used right now was for channel 38, and this one is for channel 42, which is what used to be channel 38. The digital frequencies are not necessarily the same as the analog transmitter channels. As we saw before, I mentioned some racks that we had our signals coming in from, and I will explain a little bit of that to you later, or right now. Now you can see why I'm not in front of the camera very often, because I'm not used to doing this kind of thing. This first rack here is we monitor our digital transmitter signal quality. In this rack here, this equipment right here takes the signals that are coming in from our studio downtown. Now they are what they call the hot standby system. If one or other of the receivers or transmitters fails, we'll automatically switch to the backup. These receivers here are the receivers that we use for our electronic news gathering. And these signals come in from 2 antenna arrays we have at 900 feet, and they are remotely controllable from downtown, so wherever your live truck is, you can operate them and pick up the signal from them, and they come in via these 2 receivers. The rack over next to it is, we have control for our transmitter, we have control for our tower lights. We can monitor various different parameters coming out of the transmitter, like power out, reflected power, coolant temperatures, that sort of thing. And this over here is what's called the transmitter GUI, or graphical user interface. It also is a separate system that can take the transmitter monitoring parameters and send them back downtown via our intercity links. And that way we have redundant control. So basically what you're seeing here is essentially the same thing as we're seeing there. As far as our transmitter goes, it's actually one transmitter with 2 amplifier cabinets fed by a common exciter, which we also have a backup exciter. So the power is split, it goes to both amplifier cabinets, and our required transmitter output power at the output of the mask filter is 48 kilowatts. So each transmitter is contributing 24 kilowatts to the total refined power. But because there are some losses in the signal, the transmitter amplifier tubes themselves are probably making about 26.5 kilowatts. This is the actual amplifier itself. The tube is inside of here, and it's called an inductive output tube. This is a rather old technology that was developed by RCA back in the 1930s, but the materials to make it practical were not available until the mid 1980s. This is the input cavity for it. The signal comes into here, and the tube that's inside of here amplifies it, and it comes out of this coax right here. In the bottom of it, there's a big magnet that's in here, and that big magnet keeps the beam going down the center of the tube. If you didn't have that, we'd have all kinds of fun. Speaking of all kinds of fun, the transmitter tube itself, the IoT, cost about $35,000 a piece. In order to protect that tube, we have to have another tube called the crowbar device. And this, if the tube shows any abnormalities in beam current or instances of something maybe arcing, it has to short the 37,000 volt beam supply down to zero in less than a microsecond to prevent damage to the tube. So the whole tube, crowbar tube assembly is about close to 40 grand if you have to replace it. Fortunately, they last over 40 hours. This tube here has getting close to 50,000 hours, and the one in this cabinet's getting close to about 45,000 hours. As I mentioned before, we combine at this point two signals going up the tower to handle both channel 23 and 42. As you can see by the sizes on this, the longer part of this thing is for channel 23 because the wavelength's longer than the one out of channel 23. The one that's not being used in the center used to be channel 38. Over here, coming out of the combiner, it goes from a 50 ohm source to a 75 ohm 8 3/16 inch transmission line. There's approximately 2,000 feet of this copper pipe and elbows in the system. Talking about coax, you guys all know about RG58, RG8, maybe RG213. Well, this stuff is really pretty special. It has extremely low loss. At our channel, it has 0.083 dB per 100 feet. And the total length of the transmitter line run is 0.996 dB of loss, which is pretty impressive. These devices that we have here protect the transmission line, so in the event there's an arc or something, it will shut the transmitters down. So it looks at the forward power and reverse power, calculates what the VSWR is, and then will shut the transmitters off if they're above a certain level. Behind us we have a 4 1/16 inch transmission line that goes up to around 500 feet for a standby antenna. Behind this, if you can follow me, Rex, one of the things that's really important in television is safety. You never want to be out here working on this stuff by yourself, and the transmitter is set up so that it's interlocked and protected so you can't kill yourself. You don't get any second chances with 37,000 volts. So each one of these cabinets is a line control cabinet with a lockout and a key to keep you from activating the high voltage while you're performing maintenance. We actually do a little bit more in that regard. We shut other things off because, like I said, there's no second chance if you would happen to get across the high voltage. Each tube in this thing draws at about 37 or between 34 and 37 volts depending upon the tube that you have in there, and around 2 amps of beam current. So that's about 70 kilowatts DC input for about 26 kilowatts out. So I'm coming out of the building here. These items to my left, these big gray cabinets or whatever you want to call them, are the actual beam supplies that supply the high voltage to the IoT tubes. The rectifiers inside those things are covered in oil, so they'll withstand any kind of high voltage breakdown. There also, you can, by moving some taps in the transformer, you can control the beam voltage depending upon which set of tubes you have in there. Over to my left over here is a heat exchanger. This takes the hot coolant that's cooling the transmitter tubes. They go through this thing called the dry cooler, and the temperature and so on is thermostatically controlled, so we'll either have no fans, one fan, or 3 fans running depending upon the outdoor ambient temperature. Over here, this little space invader that we have over here is kind of this is our pump module. This thing is the thing that pumps the coolant into the heat exchanger and into the transmitter itself. Now, it looks like a little space invader. Well, there's a little story behind that. Was that little white dome over the top didn't used to be on there, and there was just a cabinet inside of there that had the pump module and some control electronics for it. Every once in a while, if we had really bad weather, we'd have a problem. We'd have to replace a contactor or something like that. So Rex and I were thinking one day, you know, we got that old ENG antenna tub sitting over here. Why don't we see if that'll fit around the heat exchanger? So we did a little fooling around and came up with this guy. You can wheel it out of the way to work on the pump module, but since we've done that, we haven't had any more issues with the pump module. And it flows about 40 gallons a minute at 100 pounds of pressure to cool the tubes. As I mentioned earlier, power is vitally important to a television station. We each have 2 feeds coming in from commercial power, and we each have a standby generator. The Generac over here on the end belongs to Wisconsin Public Television, and I think that's about a 450 kW generator. The one that we have here is a 750 kW generator, and that's because our analog station used to run off of that as well, so we had a 40 some odd kilowatt analog transmitter as well as the digital. So they're both there. Our generator will pick up the load from a start. It'll take the load within 10 seconds, and quite often it starts and it'll go right to the load, and it hardly knows it's working. Coming out of the building as Rex is continuing to pan around here, you see the ice bridge, and all the transmission lines from all the services that are in this building are under that to be protected from ice. A chunk of ice falling from 700 feet will make a divot in the ground like you wouldn't believe. In fact, we had a big chunk come through the old building a number of years ago, and that was a story in itself. Our tower is actually 1,149 feet to the top, and all the TV and FM lines that go up there are pressurized with dry nitrogen in order to keep them from developing moisture problems. So the integrity of that line is extremely important to the proper operation. So if you have a leak, and which we have connected into our remote control system, we have an alarm that will happen if the tower transmission line pressures drop a certain level. So that's all very critical. Our old tower over there was originally put up, I think, around 1949. It first was used by an FM station in town, and then when later, on March 17th, 1953, it was the first television tower operation up here. And we have since removed the old batwing antenna that's not being used anymore, and right now it's just being used for ancillary services for WPNE and WIXX.